man.
Hi, how are you?
I'm pretty good. How are you doing?
I'm doing pretty good as well.
All right. We're kind of matching today. Just noticed that. Let's start off with a little thing we call...
What's happened last time?
I don't even remember, Campbell. The burden's all entirely on you. What do we do? Oh, come on. Hit start. Stall for time.
Yes.
Do something.
So we implemented the solver 3x3 and the solver 2x2. So...
Those were two rules that we came up with strategies for solving the game. Can you show us?
Which basically means if, I'm looking for an example of it.
Well, okay. There, your 5 sevens.
Yes, 5 sevens. So here, this isn't a great example because it wouldn't do anything. But in this example, here the code is saying, oh, there are two 5 sevens. Right here, we're gonna eliminate all the 5s and all the 7s from all the other from all the notes and all the other squares. So if this one hadn't been filled in, and in the notes there was like a 5, 8, and 7, then it would cross out the 5 and 8, and we would be, or the 5 and 7, and we would be like, oh, that means that there's an 8 here. So that's the 2x2 rule, and the 3x3 thing is similar, but where if we have 3, like 1, 5, 7, 5, 7. 1, 7 is a subset of it, or 1, 5, 7, 1, 5, 7, 1, 5, 7, or something like that. In the notes, then we would cross out 1, 5, and 7 from all the notes in that row and also
column and block.
Yeah. Well, not column, but whatever they're in.
Well, in this case, it would not be. Whatever the two pieces were. Part of. You're right.
So here, like, if there are any 5s or 7s, I don't think there are.
I don't see it. I think maybe we jumped in a little too late in solving the game to see it. I think we'll see them a little sooner if you want to try it again.
Yeah.
Because what's happening now is our 2x2 rule and our 3x3 rule are actually working right now. So they're finding places. We're also finding, and you might have to load like the medium level game, as I recall too.
Yeah, I did.
Okay.
This is the medium level game. So here you can see there's a 5 and a 7 here, but if I hit solve, wait.
No, because we solved with 1, 5, 7,
yeah,
so it doesn't matter.
Here, 5, 7, 5, 7. The 5 and the 7 went away from here and all of these.
So that's the 2x2 rule,
yes.
Already taking it in. I see what you're saying. Okay,
and
yeah.
The 3x3 rule. Oh, yeah, right here. 1, 7, 8, 1, 7, 8, 7, 8.
Yeah, there's nothing else in that column, though, or in the block to take out. But if there were...
No, I think we already solved this.
Oh, you think that did? Let's go back and try it again.
There. Oh, wait, I wasn't looking at it.
It probably happened on one step. The 2x2 rule one rule took... Go ahead, what do you want to say?
So here there's the 8. So if we keep on looking, see the 8 went away, and the 1, 7, 8, 1, 7, 8, and 7, 8 rule got implemented. So yeah. Okay,
I see. So yeah, what's happening is every time we hit solve, we're applying our 2x2 rule and then our 3x3 rule in one step.
Even here, there's the 3x3 rule. 3, 4, 3, 4, 5, 3, 4, 5.
Right, and last time we also noticed that the number of clicks of the solve button went down as we added our 2x2 rule and we added our 3x3 rule.
And that's in our regular game.
And the first thing we did is we just basically said, hey, look, if there's something, Creature Next is out there. Welcome, Creature Next. We also have something that just basically is using kind of process of elimination, that sort of thing. If we see that an 8 has to be in a particular place, then we take it out of all the others. So it's kind of a 1-by-1 rule. So that's what we're doing so far.
So here in this block, it sees 8 can't go here, here, or here, and it also can't go here, which means an 8 has to go here. And you can see that solve. Well, a 6 can also go there, but it should eventually know that the 8 has to go there once it finds out. Yeah. So now if you see 8 is the only note there, once we hit solve again, that gets filled.
What's interesting is it didn't find that at the beginning, which indicates there's still probably another strategy
rule,
that we could implement automatically. But we're not going to do that today. We're going to do a brute force kind of what we call kind of a brute force attack. We're going to use recursion to create a solution.
Yeah, so it's 6 clicks for the easy game.
Say that again?
6 clicks for the easy game.
That's how long it takes now. And it used to take...
I think, 11 clicks?
11 clicks to get it, to solve it. And so that's kind of where we are. And
we also, after the show, we found a bug where we weren't implementing the 3x3 rule and the 2x2 rule in columns because we were calling it on column when we had already done it for column. We just needed to call it on row.
Yeah, we changed the word column to row in one of our iterators, and it fixed the bug. All right, cool. Let's switch over to my machine.
Okay.
I want to get this up, and I'm going to actually run this and show you. I want to talk about stacks. Stacks are like a list of T. That's how we say that right there, Campbell. It's a list of T. T means a type, so a list of ints, list of strings,
a list of floats, a list of
a list of Sudoku squares.
Yeah.
Okay. The last one in the list is the first one up. Yeah, it's a little bit hard sometimes to think about that, but I'll give you a demonstration. I'll show you with kind of a visual, and then you'll kind of get that. We use peek to take a look at what's on top of the stack. No changes. We just take a look at it. What's there? We use push to push new entries on the stack. We just stack them up.
Yeah.
We use pop to take away the most recent entry.
One.
Okay? So here's some visualization. What'd you say?
That's pretty straightforward.
Up here I've got a line of code that says var my stack is equal to new stack of int. Now we haven't seen the var keyword yet. The var keyword is in place of a type here, and it's kind of a very kind of automatic type is what it is.
I've seen it in, I think, in another language.
It's in, and yes, and it's in C# as well. And if we use it, it means you figure out the type. I'm not going to tell you what it is. And if it can figure it out in the initialization, everything will be fine. The compiler will say you're good. So basically it says, oh, I know this is a stack because it's a stack of ints because I can see what you're doing over here.
Wait, so it's kind of like, not really, but it's kind of like the thing that says we're not going to implement it here?
Yeah, a little bit maybe.
But
not
the code
really.
It's
basically, it's kind of a, yeah, it's conceptually a little bit similar. So this line of code creates a new stack of what?
A new stack of ints.
Right. And the stack is empty. So executing the line of code, my stack looks like this. It's a big empty rectangle. Okay? Now we call myStack.push4. MyStack now contains one entry right here.
Yes.
It's oldest and most recent.
So if you try to take one off, you're going to take the 4.
Exactly, and then it would be empty if we popped it.
Yes.
Okay. We push again. We push number 3 on. It looks like this.
So if you want to pop, you take 1 now.
Yeah. And then, and I can even, I've been pushing 4, 3, 2, 1, but I can push any number I want because it's a stack of ints.
Yeah.
Make sense? And important to know, I can stick anything on there, right? I can put cookies, a stack of cookies, right? It can be a class, it can be a primitive like an int or a boolean, whatever I want to store on the stack. If I call pop, the most recent one comes off.
452.
And now what happens is this line of code here, look at it, int result equals myStack.pop. Result will be set to the value
452.
452.
Yeah.
452. Okay? It's a great way for storing things and coming back later and looking at them. If I call stack myStack.peek right now,
we'll
result
see that it's 1.
Is going to equal to 1.
But
okay?
You will still, if you try to, if you peek again, you'll still get 1.
Yes. You peek 100 times and it'll be, what if we peek 1,000 times?
It will always be 1.
Okay, but what if we did it 1,001 times?
It would always be 1.
You're right, but what if we did it 1,002 times?
It would still be 1.
All right, next slide. Or do you want me to keep drilling you on this question?
I think I got it.
All right, so there's also something called the call stack. It's different from a regular stack. It's the call stack. When we run a program, the call stack keeps track of where we are in the code. When we call a method, anytime we call a method, an entry telling us where we were, and anything else we need to resume code there gets put on the call stack. So we know where we call it came from. We know who called us, all of that. It's on the call stack.
Yeah.
That happens when we call a method. So if the stack grows whenever we call. When we exit a method, that entry gets popped off of the stack.
Ah.
Okay? So what happens when we start a program, the stack's pretty much at 0. And as we start calling methods and getting deeper and deeper, calling methods more and more, deeper, not sequentially, but deeper. One method calls another and another and another and another method, and it calls another method, right? That grows.
So in the method, you call a method, and in that method you call,
another method. And if we get a breakpoint there, we've got like, a couple things on the call stack.
And not just if you call a method and then you exit the method and then you call a method and then exit.
Right, if I call and exit, then it doesn't grow. It just pops up and then goes back down. When execution stops at a breakpoint, we can see the call stack in the call stack window, which I think the shortcut is Control-C. I didn't double check that. That's from memory right there. But the call stack window would show it to you visually. We'll take a look at that in a second, I think. All right, let's talk about recursion now. Recursion is when a method calls essentially back onto itself. The method calls itself. So I'm inside the method and I call back out to go back inside the method again from inside the method. It's a little mind-blowing, right? You kind of have to build new structures in your mind to envision this and think about this and be able to write code for this. There's two components to a recursive method. One is it needs a condition check, some way to exit the method to get out without calling itself again. Because if the method only calls itself, Campbell, that stack will grow until it hits its limit.
Something like an if statement, the return, or
That's what you were talking about, like that, a condition check, some way to exit without calling itself. So it needs to have that. Another way of doing this is you have a method that instead of explicitly exiting, it just explicitly does a condition check and only does the recursive call if the condition is satisfied. Because if it doesn't do that, then it'll just fall out the end of the method and it still exits the method. See what I'm saying? We just need a way to exit without recursion. Some way to do that.
Yes.
And we need a recursive call back onto itself. The result of the call typically determines what we do next. Like we might be looking for something, for example. And so the result might be, we found it. So if we're looking for something and the result of the call is we found it, then we know we don't need to continue.
Okay.
Recursion lets us drill deep and wide into a complicated structure, like multi-dimensional array or an object graph. This is a picture of an object graph here where I have like a parent, this is like, imagine a friend network where this is you and these are your two friends and this is your friend and this is your friend's two friends and this is your friend's friends, two friends right here, that sort of thing, right? And if I want to search through and find how many of these people know you, I would go through each one. I would be able to get these. One of the best ways to do this is to use recursion, where we basically put a friend in as the parameter, and then we go through, iterate through its friends, and then call the method again with each of those friends as a parameter. And then we just write a little bit of code that goes through the whole thing. And that's it. Recursion lets us do complex things with very little code.
Very little code. Because it's kind of one method that does it all.
Yeah, it's one method plus a caller. Somebody's got to start the call from outside. So somebody's going to call that one method. But that's it, So here's a challenge. We want to stack a bunch of blocks. We can stack one block on top of the edges of two blocks below to create a pyramid. Whoops. Like this. And we can continue that to do like this. So our challenge is to build a recursive program to calculate how many blocks are in a pyramid having a base 20 squares long. All right, and to do this,
well, I would imagine the method would be something like,
well, let's build it.
Okay.
So to do this, I'm going to, let's split our screens here. I'm going to create a new project. Before the show, I had Campbell create an empty project. Go ahead and open that up. We need a console app, .NET Framework. Call this first recursion trial. So it matches Campbell's. We're going to create this. I'm not really going to need to worry about saving this or anything. It's just kind of a throwaway project so we can kind of take a look at recursion.
Yeah.
So we want to start with, I think it's always good to kind of start with the client code. Here, I'm going to zoom up and you might want to zoom up a little bit too. Make sure your font's easy to see so people can see it. So the first thing I'm going to do is I'm going to say, I'm going to type in VI in space and I'm going to type in the word answer like this. And then I'm going to say that and I'm going to call it get pyramid block count, and I'm going to pass in 20. Like that. Then, once you type that in, I always have to think when I'm typing in pyramid.
Oh, did I get that wrong?
Okay. I'm going to block count, and I'm passing in 20.
Oops.
Actually, let's do this. Let's actually, instead of passing in 20, let's pass in 2. Okay, and on the next line, let's type in console, console right line, so it's CW, there you go, like that, CW. Let's do an interpolated string, and let's say, make it be a pyramid with a base of has blocks. So we're hoping it better be 3, right? Okay, cool. You just put the number 3 here if you want. We can do that too. All right, good. All right, now let's declare get pyramid block count. Now what we've done, by the way, I call this kind of it's kind of like client code driven development. In other words, it's development that's driven by the client's perspective of the method. So instead of going in and writing a method first, which we could have done, I instead wrote the code I want to work and I wrote the code that I want to use in the way I wanted it to look. And then that informed what the name of the method is and what parameters I'm going to need to pass into it. So let's go ahead and declare that.
Generate method.
And inside here, so now what do we have to do here? We need a condition that says whether we call back into it or not. And we also need to return a result. Let me ask you this, Campbell. If value is equal to 1...
that's not what I wanted to do. If
value is equal to 1, what are we going to return? Oh, you want to say v instead of value because your variable is declared as v.
That's what I wanted. Okay.
You just say v equals 1 because that's your variable name. See how yours is different from mine? I have value up there. You can hit the coder scheme, choose rename if you want. Rename it to value. All right, so if value is equal to 1, what would we return? think about it. If I've got a stack of 1, if the base is 1, how many blocks are in that pyramid? Maybe that's what I should have asked. Right? 1. That's always what you want to be thinking about that when you're looking at the code, right? If I ask which value is 1, what do we return? Really, you want to be thinking, what does this do? Get pyramid block count. What's he really asking me? He's asking me if value is 1. What he's really saying is if the number of blocks in the base are 1.
Okay, so yeah, 1.
Okay, so let's write that code. You can get when you get down to this line here, just type in R1. Coders will build that in right there. Okay, so cool. If the value is 1, now one of the things that just occurred to me is value. It wasn't really clear what value meant, right? Do you know what value is?
Yeah, it's the base.
Number of blocks in the base.
Yes, sorry.
In base. So now I'm just renaming that to number of blocks in base. If you want, I'll got it on the clipboard. I'll paste it in over here so you don't have to type that in again. Well, I said I would. It's not there. Blocks in base. Okay. All right. So if it's not 1, can you think of what we would return? And before if you're not sure, let's switch back to my machine. I want to show you something. Are you not sure, or do you have a sense of what it is?
No, I'm not sure.
Okay.
Oh wait.
So if I pass in the number 3, like this, or maybe even let's talk about 2. If the number 2 comes in, this is equal to the number 2 plus the number of blocks in this base,
which is that number minus 1.
Right. So exactly.
We would return the number of blocks in base.
Hold on.
Plus.
It looks like Campbell's going to write some code. What are you going to say?
Okay. So
we want to return something. What do we want to return?
No.
This would be really impressive if you get this. Okay, you're looking good so far. This is not an easy thing to figure out. Yep, the plus is right. I agree with that as well.
Wait.
Not a plus equal, so it's
just
a plus.
And then
what? No, you're close, but that's not it. Cut number of blocks in base minus 1 to the clipboard.
Okay. Wait.
It's not that, because then you'd just be done and there's no recursion. Where's it going?
Wait,
need a space there to get IntelliSense. Where's it going? Look at this. Look at this. End key. Look at that. Nailed it. Semicolon. I think that's going to do it. So let's run it, and it might go away real quickly. I think we might have to do a console.readline at the end of this. So I'm just going to copy console clipboard and say readline like this. So it just waits for us to hit enter. It won't close everything.
Oh, yeah, it did.
What'd you say?
It did.
It did what?
It closed down immediately. Oops. Control C.
Okay, I've just done the same thing. Now we've got a recursive call. I'm going to run mine. And this is what I get. Right in there. And it looks like it worked. Did you get the same thing?
Wait, let's see.
Move it over to the right a little bit. Yeah. That is 3 blocks. Cool. So now we can answer the question. We can do one more test if you want. Once it's here, if you want to close the program, I think you can just hit enter. Let's change this up a little bit here. I want to make a variable called base. And I want to set that equal to 2. Like that.
Yeah.
What'd you do?
I did 5 and it got 15.
That looks right to you?
Yes. That's what I got.
Why does it say there? Oh, you know what's going on? Look what it says though. The pyramid with a base of 2 has 15 blocks.
Ooh.
And then 3 in parentheses. So here's what we want to do. We want to change this up.
We have to make this a variable.
Yeah. I want to create a variable called base blocks here. And I'm going to pass it in here. I'm going to pass it in, yeah, set it equal to 5 or 2 or whatever you want it to be.
Equal to 5.
Okay.
And then here we'll do base blocks.
Semicolon, don't forget that. Yeah, exactly.
Oh.
Exactly. These blocks, and then we have to change it in one more place.
In the interpolated string.
Right. And then I'm going to get rid of my better be 3 because, you know.
It's not needed.
Yeah. And so now I'm going to come in with, I'm going to throw 20 at it. Control space should get it to finish it up through. And get rid of 3 at the end. You don't need that 3 in friends anymore. This is one of the easiest bugs to introduce, by the way, Campbell. A bug where the display tells you something different.
Than what it is?
Than what it is, yeah. Save it and run.
Yes. Also, it's very reproducible. Yeah.
All right, base 5 is 15. You want to be the first to find out how many blocks are in a base of 20?
A lot.
It should be 15 plus 6 plus 7 plus 8 plus 9.
210.
210 blocks. All right. So that's recursion. It's a way to solve problems. Okay? Any questions on that, Campbell?
No, I don't think so.
Okay. Do I have anything else on the slides? I don't think I do. Let's see. Nope, that was it. All right.
Oops.
Now we got to go back to our Sudoku program.
Okay.
Let's go do that. Let's do it on your machine. I'll bring it up. I'll bring your machine up full screen here.
Okie dokie. Should I? Yeah, I think I'm going to create a new class.
I almost want to run this a second. Let's talk about how we're going to. When are we going to do this? Right? In other words, our current solve algorithms are not bad. Right? They work pretty well.
So here, in this moment, when if I hit solve, it doesn't do anything.
Can you do me a favor, Campbell? Can you go back to that state you were in before where we were looking at that upper right corner in block 2? And we were saying, why didn't it know immediately that there shouldn't be an 8 there? Can we go look at that again?
Yeah.
I just want to understand that a second.
No, because it's calling the 2x2 or the 3x3 in the same click of the solve button as it's doing all of the other solve.
Yeah, I don't think it was this one. I think it was another one where you were looking at it and you said, oh, this has to be an 8 right up there.
Oh, wait, and just the regular one. Yeah, here, because the 8 can't go here or here, and it also can't go here, here, or here, so it has to go here.
Right.
But our code doesn't know that until, wait, but here's the weird thing. Ready? Watch this. So a 6 should fill in right here, right? And then that should make it so that we know an 8 has to be here.
Yeah.
Right? And then the notes switch.
To a 2.
Yes.
How do we get a 2 there?
I am not sure. Wait, let me check something again. Okay, so if we hit solve, all right. Right here, there's nothing blocking it from being a 2.
So there should
why
be
does it put a 2 here?
There should be a 2 there.
There should.
Unless one of our 2x2 rules got in and cleaned it up. That might have been what happened.
It would clean. If it were to clean it up, then it would have cleaned it up from here, the 2.
Well, it cleans it up now because the 2x2 rule is applied, but after we start filling things in, it gets rid of the 2x2. The 2x2 rule no longer satisfied, so it doesn't get rid of the 2. I think that's my theory on why the 2 comes back. Kind of interesting.
Oh, a 3x3 rule. 1, 2, 5, 2, 5, and 1, 5.
Yeah, but no 1 or 5 to remove from the others, or they've
No,
already
it
done
probably was, but just in the last
Okay,
step.
yeah. All right, so what's interesting about this 8 up here, this is the thing, in block 2, that 8 right up there, really kind of interesting. Can you move the yellow highlighter over to that?
Yeah.
So we've got to focus there. So this is interesting to me because out of everything in that block, it's the only one with an 8 in it. we should know that's an 8 immediately. We don't have a rule that does this. And this would be actually a pretty interesting rule to add. I'm not sure if we want to go right, if we want to add this or not. This is kind of like a rabbit hole where I'm saying, hey, look over there. Do you want to jump in that hole instead? Or would you like to go for the recursive approach and solve the whole thing?
I think we should do this rule, maybe. Yes. I think we should do this rule.
Okay.
Just to see how much faster it gets.
Okay, we can do that. All right, so we're going to call this the only one rule, maybe? That's what I think we'll call it.
Maybe.
All right, let's do it. So let's close this down. So we've been creating our solvers. They look like this right here. And so all I think I'm going to do is I think I'm going to go find my 2x2 solver.
If you think about it, there's kind of also a solver 1x1 that is our first rule.
Right.
Where it's that if there is only one number in a 1x1 space, then in a 1 space, then, eliminate it from all the others.
Yeah, no, I agree with you. All right, so we're going to call this the only one solver, maybe?
Yeah.
Like this, it's going to descend from base group solver. We should be able to implement that abstract class. That throws us the solve method right there. And we want to tap to next reference on this. And duplicate that and
only one solver.
Add that one right there. So that's going to run that. The only one solver is going to look like that. And so then let's move type to file so it's in its own file. And here comes the group coming in. And so we're going to say we're going to have to iterate through the group like that. So we're going through 0 through 9. This is a group of 9. And we're going to check to see, we want to see if we want to count up all the digits found. And if there's only one in the notes, right? So I'm going in the notes, counting up all the digits found. Total of all. So I'm going to count how many 1s I have, how many 2s I have, how many 3s I have, how many 4s I have. If I have only one 8, then I'm going to go find out which square had the 8 in the notes, and I'm going to make it an 8.
Oh, okay. So.
And I'll clear the 8. Well, I won't have to clear the 8 out of any other notes, because they'll be gone.
Yes.
Right?
With our other rules, they'll.
Yeah, so to add all these up, I need a dictionary. So I need a new dictionary of int-indexed ints. Like that. New dictionary of int-indexed ints.
Oh, okay.
Like that. Okay? And these are going to be numbers found. Like that. And so for each number, we're going to count how many we found for each number. So we created that, and then we're going to do this. We're going to say we're going to get the element of I, which is going to be that Sudoku square right there. Sudoku square, and then we want to get its notes. So we want to get its notes. And I think there's an ancestor method called getNumbers, where we can pass it in string notes, and it's going to return back a list of numbers. So this tells me all the notes. I'm going to call this notes. Okay?
Okay.
Do you understand those 2 lines of code?
Yes.
This group of I is just from the iterator here. So we're going to just grab each square. We're going to find out what notes it has. Now that we have the notes, we're now going to do this. We're going to say, hey, we're going to do a for each, and I'm just going to put the word note right here. Okay? For each note, it's going to be an int, in notes. We're going to check to see if numbers found has it. So So we do, hey, if not numbers found dot contains key, if it doesn't contain that note, then we're going to say numbers found dot add. We're going to give it the note, which is the key, and we're going to give it a count of 1. So it doesn't contain it. If it's not in the dictionary, we're going to give it a count of 1.
Okay.
You got that?
Yes.
Do you agree with that?
Yes.
Okay, what else? We're going to do this. We're going to say numbers found of note, and I think I can do this in C#. And say plus equals 1. We're just going to increment the count in numbers found.
Okay.
Okay?
Yeah.
So if we find it a second time, you know.
Couldn't you just plus plus?
Looks like I can. Cool. Okay? You with me?
Yeah.
So far. Okay. So cool. Next. That's going to go through final numbers. Next we want to go through all numbers found. So we actually want to go through all the keys to numbers found. Why am I not seeing that's the method? I'm outside the method. Okay, here we go. Numbers found dot keys. I'm going to take that, copy it to the clipboard. I'm going to type in FE for 4H. And it's going to go through all those. Remember, these are keyed by the note, right? So for each note in those keys, I'm going to check the count. If numbers found of that note is equal to 1, then we're going to say magic, kids. We got some magic happening here. What's happening here is
not magic code.
What? What?
Not magic code.
Okay, fine. It's code. All right. So it's some code, kids. Code, kids. All right. At this point, we know that note has to be here. Has to be in this square. We don't know what square it is, but we know note the 1, 2, 3, or 4, whatever it is, has to be in the square that's in that note because it's only got one of those. Okay? So now what we want to do is we want to go through the group again and find it. So come back over here. We're going to iterate through the group again. I'm going to copy this line of code too, so we can get that Sudoku square there. Then I'm going to check, I'm going to go in and get its notes as well, just like we did before. We actually need the same kind of lines of code right here. Call get numbers on it. And I'm going to say, hey, if notes dot contains note, it's only one, and we might want to rename this here just to be, we might want to create a new variable here, call it only one note, just so it's easier to read the code here. I'm just going to create a new variable called only one note and set it equal to note. Does that make sense? So now we're going to say, if notes contains that only one note, then now the cool thing here is now we know the square.
That's true.
Okay, now that we know the square, we can make some calls on it. Any ideas on what we should change?
We need to change probably the notes first, and then also the actual value of it. What is that called?
It's called value.
Oh, okay.
See them right there? All right, let's do value first. We'll do the other. We'll add the other one before in the line above this. But what are we setting value equal to?
Only one note.
Yes, that's exactly right. We said it's only one note, and we need to do a toString on it. Is what it looks like we have to do because it's an int and value is the text, I believe. Whoa, whoa, whoa! There's no setter on value. Campbell, our solve didn't include or the ability to set a value when we built our interface. So we go back here to our interface. Whoops, sorry.
Oh, then we're going to have to change your interface.
Yep, we're going to have to change our interface is what we're going to have to do. What's not getting that? Is that just not selected? Let's try that. Not finding? Why are you not suggesting that? I think that may be an option I need to turn on. There we go. Let's go in here. It's missing a setter. I say we do it.
Okay. As long as none of our other code depends on us not having a setter here, which I'm assuming it doesn't.
I think we're going to be okay. So what we need is a setter. So I'm adding the setter right here. And we're going to do this. We're just going to basically say, hey, the text is equal to the value dot toString. Because a char is not a string, but if I call toString on just on anything, it'll turn into a string. Okay, so I'm going to do that.
Okay.
And so now we should be okay here. Oh, but now, holy cow, it's not a string, it's a char, which means we need to get this into a character. Easiest way to do that is to say, take character number 1, the first character from it. Since we know it's going to be a single digit.
Oh yeah.
Right there. Now, it's occurring to me that I think we wrote some code that is not going to work if we change our available digits, symbols, from numeric outside of numeric.
Oh.
Okay. Because we've got this call to get numbers, we're expecting to get a list of we'll have to change this to get symbols for this to work, and all the code that works with that, make that work. All right, so there's that piece. Now we know we need to remove notes from this, so we're going to say notes.remove, and we're going to pass in only one note, like that. And then we're going to say that removes it from our local list, and then we have to set it here. Notes is equal to probably just notes. We're going to do that. We need to get this back into a string, and there's that function called join. That'll do that. It'll put a comma between all of the notes right in there. So what I think we should do now, at this point, we need to return a result in here. I'm going to set it equal to, by default, solveResult.none. And then down here at the end of the method, we'll return the result. And then right here, we know we've made a change. I'm going to say result is equal to what?
Result is equal to is this one also?
It's suggesting solve result. It's an enum. You can see by that piece right there.
Oh, that means enum.
And then if we hit a dot here, which of these two do I want to send this to?
None, right? Or no.
Nope. If I do none, then it won't know it's been solved. We've made a change. This means we've made a change. Square solved. So it's that one right there. All right, cool.
Okay.
Let's run it and let's set a breakpoint in here and just step through it and see how it works. Okay?
Okay.
Make sure we get there. So go ahead and run it.
Sorry, I just needed to save that as well. So here.
All right, so we know we're getting called, which we know that means our solver's been registered. That's cool. We did have 10. No notes. Nobody's got any notes. Okay, so this first time in, we're not doing anything. I'm going to set a breakpoint in here. So, and that'll stop us the first time we find some notes. Oh, we found some notes. Okay, this has got one note and it's of 1. Okay, cool. So it's just going through each entry in and it's collecting all those pieces. Let's set a breakpoint here and run to there. How many keys do we have? 4 keys. Looks like each of those just contain, oh sorry, wait, those are the keys. Numbers found. There you go. Here's the numbers found. See them?
Yeah.
1, 2.
1, 2, 9, 1. 3,
so there's
2,
1, 9
3, 2.
out of all those, and there's 1, 3 out of all those. See it?
Yes.
All right. So what that means is we should get to here. When I set a breakpoint there and run, we should get to that point. Cool. There's the 9. And if I hit F5 to run it, we should get again another break. Oh, I thought we were going to see the 3 there. Okay. There's an 8. So we found the note of 8. Only one 8 found. We're going back in to try to find it. Let's see. This is where we find it. So now we found it at index 7. So group the Sudoku square at index 7, the 7th one in.
Is 8 just?
What'd you say?
It's just 8, right?
It contains only the note 8.
Yes.
So we're going to go into its notes, which are currently have 2 notes, 7 and 8.
So we need to remove 7 because we know that it's just 8. 8
right,
is the
exactly.
only 8.
Yeah, so we're going to remove that. So now the note has only 7 in it. Then we're going to set it back to that. So there you can see the string there. And then we're going to now convert the value to 8. Sweet. And we're going to say we solved something.
Woohoo!
I think this is going to work. All right. It doesn't look good though.
Uh-oh. Wait a minute. Ha!
I don't like our rule, Campbell.
Yeah, me neither. I mean, at least it got the 8 in the right place.
Is that what it did? How did it go to the 4s, I wanted to know. That's like, that's kind of interesting. So, and why does it put multiple of them in? That doesn't make sense. It must have found them in 2 different rule sets. It also feels like the notes may not be
I think
correct.
we're just checking for one thing. I don't think we're checking for the block.
Let's try this. Let's try this a second.
Yeah, I don't think we're checking in the block because all of these errors are coming from the block, I guess. I think.
No, we have to be, we're called. We are called. We already know the other ones are working and are checking for rows, columns, and blocks. I have a theory on this. My theory is that this solver will work if the notes are correct, but won't work if the notes are not correct. I have a feeling they're not correct. I just want to try this. I want to put it first, so it's the first one we ask.
Okay.
Let's run it again.
Nope, it only fixed the 4. But look, the notes are wrong. This 4 isn't allowed to be here.
Yeah, our notes are not good. All right, let's take
that 3, and wait, look. This 2, 4, and 6, this square should have no notes.
You're right. All right, so we've got just a bunch of problems. Comment it out.
Okay.
I don't want to investigate this right now because I'm like, I think it's a little beyond my pay grade right now. My mental state. You can go ahead and run it if you want, and we'll go back and verify everything's still working the way we're expecting it to. Got to figure out that one solver. What's going on with that? Why didn't that code work? Or what's wrong with the data? There might be a problem with the data.
Nope, everything still works. Okay, that's weird. Well, all right.
Can we go back actually and run it just like this? I want to see. Remember with this one when it was at the end, it got the 4. It got those 4s in the bottom of block 2. Choose solve once. So in the bottom of block 2, if we look at this, there's a 4 here and there's a 4 here. There should be a total of 2 4s found when we evaluate this block. When we evaluate the row, there should be 2 4s found as well. When we evaluate this column, only 1 4 is found in this column. When we evaluate this column, 2 4s are found.
3.
3?
Yeah.
So this is where the 4 should be. Because the column row should find it.
Oh, I think I might know what's happening in that situation. Look, 2, 3, 3, 4, 2, 4. This is the 3 by 3 rule. I think it is, at least.
Yeah, but if that's 3 by 3 rule, it doesn't change the 3 it's found. It only changes the ones outside of it.
Oh, that's true. But,
now I'm back to curious about this again. I kind of want to get in. I want to get to this particular bit of data and look at only this data is kind of what I want to do. Let's do this. I'm going to take a screenshot of this. I'm going to start up Paint on your machine. I'm going to paste the screenshot so we have it as a reference. Okay? Is that you understand what I'm doing?
Yes.
Okay. I'm going to close this down. I'm going to re-enable our only one solver. We'll add it back. We'll put it at the end like we had it originally. And I think I'll start, let's see. So this is how we do, this is how we iterate right through the solvers. I'm going to go ahead and run this now. And can you load the game? Which game do we load?
We loaded the easy ones. The easy one for others.
All right, cool. So Campbell just hit solve. We're going through all the solvers. There are 3. Okay? We want the last one, the third one. So I'm just going to hit run, and now Sudoku solver, now this one is the only one solver. Got it? Now we are interested in the second block, which is in this space here. Got it?
Yeah.
This is where we want to be. I'm going to ignore everything else. Just run. Now, we seem to have found one node in the numbers found keys. This is interesting here. I think I want to do this. I'm going to say return result for now.
I think I have. Wait. Sorry. I think I might know how we can fix this. Maybe. And that is to call all 3, get row, get column, and get block, like for the for this only one solver thing, from one method in this class. So then it will call them all at the same time, and then I think it will see, is it, no.
Oh, I see what you're doing. It's kind of like saying, let's focus on the square and call it for all of those.
Yeah.
Yeah, I feel like if the notes are right, the logic feels like it should be working. That's the thing I want to verify. What I'm going to do here is I'm just going to do this. I'm going to get out of here fast and early until we get to the block, because I want to not change any data until then. So I'm going to run until now we're down in the block. So we're at the first block right now, block 1, which is going to be R00. I don't care about that. I'm still returning. And now we're going to be block 2, right? Row 0, column 1. Now I care about it. Okay? So now I'm going to go into the solver, get rid of this line of code, and set my breakpoint here. So now I'm looking at that block, right? Let's refresh our memory over here. I'm looking at this block. And inside here, I do not have only one 4. It's in the column that I have only one 4.
Oh, I think, look, can I have control of the mouse?
Mm-hmm.
This rule is a bit flawed, I think. Well, yeah, of course it is, but also, we can't just check to see, wait, I was thinking, sorry, this isn't really a problem with what.
Oh, I know, I think I know what wait.
But I was thinking if we checked, is this the only note in the row, column, and block? But
you also have to check against the other numbers that are there. We're not checking against those numbers, Campbell. Does that make sense? In other words, it has to be, in other words, I have to also check to make sure there are no other 4s inside of there, right? If I have something that's a 4 or a 3, and that's my notes, but I've already got a 4 in there, nothing's going to stop me from putting a second 4 in there. That's the problem with our logic, and I think the destruction of the notes is happening here as we're going through it. That's kind of what my feeling is. So we need to do this. It has to be in the square. We have to both find the square, but also check to see if anything in the group has that value. So if notes, so basically we get to this point where we're like, only one note is here, right? We need to check to see if group already, we don't have something, it's like a static, I think, in the base. Base group solver dot note counts.
Wait, what are you doing right now?
What I'm doing right now is I'm checking to see, thanks for asking that. I'm checking to see if this only one note, whatever this character or number is, that it does not already set in the group. If the group has it set, then I don't care if there's only one of these in here. One of these in here only matters if there's none other in that group. If there's only one 4, for example, in a note, it doesn't matter if the 4 has already been set somewhere else in the group. And that can happen, I think, as we remove and update notes as we're going through and solving. I think my theory is that the solving is causing a destruction, and that's why we're getting 2 4s showing up when we shouldn't at all. So I want to do this. I want to say, hey, if group already is showing only one note, then I just want to call continue. We're just going to continue, go up to the 4 each and keep going. That's all I want to do. And I want to pass in the group as well. Like that. That's what I want to do. I'm going to copy this code right here, and we'll implement it. Group is already shown. Paste in that code. So we're going to go through the group, get the square, and we're going to check to see if the square's value is equal to only one note, 2 string, first character, which I'm going to now introduce a variable for this thing. Call it note char, maybe. Let's bring in this from only one note to note. And we don't need to do that every piece of the loop. We can do it before we get to the loop. Okay, so now what we're going to do is say if the value is equal to note char, we're going to return true. And down here, we're going to return false. We didn't find it. So we're just trying to see, does the group already have this value? That's what we're looking for. And I'm betting you we're going to hit a return true here if I run it. So I'm going to clear this. Let's see, do we get to the return true? We don't. Okay, but we haven't done anything yet, though, it looks like. Although we got an 8 here, and it didn't take away the 6, unfortunately. That, I think, is another bug somewhere else.
And same thing down here. Didn't get rid of the 7. Didn't get rid of the 3, 4, and 6. This wasn't happening before.
But it did get the 8. Let's try again and see what happens. See if it gets this 4 this time. You want to hit solve?
Yeah.
Ah, now we got it. Hit run. You might come back and hit it a second time. Yeah, go ahead and clear the breakpoint and hit run. So now this is the problem we were talking about before, because I think the notes aren't being cleaned up properly.
Yeah,
so we got
look, because I think I know what happened. So because the notes weren't being cleaned up, so because we weren't cleaning up the notes, in here there were 2 numbers and each of them had a 9 in their notes as well.
Yeah.
And there was also a 9 in this one's notes. So they used our other rule, the solver 1 by 1, if you will, and it was like, oh, that means that a 9 goes here, here, and here.
Yeah.
When that was wrong. So all we need to do is clean up the notes, and I think it will solve it.
Yeah, I kind of agree. Why are our notes not being cleaned up? If we disable this rule, do the notes look good? That's my question at this point. Let's comment this out when we add it, and let's watch it and run it and see if the notes look good. Can you look into that? Try it. See if you find any problems with our notes.
Nope. Look, so far no problems. No. Nope. 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 No problem.
So we are destroying the notes. We're doing something wrong here on our notes. When we call this, we are doing that. Let's go look at, where is it? Only one solver. Let's look really closely at this. We're setting it here after we remove it.
Yes. No problem.
We're setting the value. I think I see the problem. It shouldn't be notes remove only one note. So it shouldn't be notes is equal to this. It should be notes is equal to that. Because we know the value. We were kind of essentially just removing the 8 from the notes and keeping whatever else it had. And then it was saying, okay, well, I can now still work with it. Try it now, but wait, let's make sure we're now uncommented. Try it now. Wow. Wow.
3 clicks.
Wow.
3.
Load the hard game.
Wait, the medium game?
Do the medium. Do the medium. Fine. Do the medium.
Yeah. Okay. This is the medium game, right? Yes.
And it's, wow, it's still going. And then it's stuck.
That's when it stopped.
It's stuck there. Okay, that's really not bad though.
What about the Control-Shift load game? I don't know about this one.
Yeah, I don't think we're gonna get much of anything here.
Oh my god! We got nothing.
Oh my god, that's the hard game or that's the medium game?
That's the hardest game.
Wow.
And we had nothing before, and then we implemented that rule, and now we've solved it completely.
It's crazy.
Wait a minute. Am I sure this is the hardest game? Yeah.
Yeah, that's one with very few squares. Okay. All right. Well, I'm glad we went down this path, Campbell.
Me too.
Thanks. It was a good suggestion, I think, to go here. Cool. All right, let's go to recursion.
All right. We might not finish it in this show, but we still have tomorrow.
Actually, I want to run in a second. Let's talk about when we're going to do what's the game that we can't solve?
Control load game.
What is it?
Control load game.
Control load game?
Yes.
Okay.
It takes a second to load up, but.
All right. Solve. 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 So we take it to here.
This is when we want to start doing it.
Now we want to do recursion at this point. So what I think we want to do is add a new button that says recursion, or super solve, or brute force. You decide what we're going to call the button. We add the button.
I like brute force.
Okay, so we're going to call brute force, and then we'll just call it brute force, I think. That's cool with you?
No, we don't need the ignorance, but...
Yeah, we don't need ignorance in that. So we're going to run that, and then what it's going to do is this. It's going to go through it's just going to iterate through every Sudoku square in the grid. It's going to ask this question. Are you empty? Are you empty? Are you empty? Oh, are you empty?
Yes, you are.
Then let's guess a value based on one of your two notes here.
Yeah.
Okay?
And then...
It's not going to guess them all. It's going to be smart. It's going to see what its notes are. Then it's going to go call itself again. But now that it's going to fill the value with a yes, and so now it's going to go, are you empty, 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 empty? Now it's going to go here. Not empty. I'm going to try a 1. Right? Then it's going to go through all, going to try 3 there. Right? If it has any problem, if it get at any step of the way, if it breaks something, if the change breaks something, if the square is broken, if it has conflicts, it's going to return false out of the method, and it's going to reset this to a 0 state. Is what it's going to do.
So I think, this code might actually be easier to write than.
I'm not sure what it's going to do with the notes as it makes a try. I think it's going to call it a trial. We're going to maybe need to create a new flag in Sudoku square called has trial value, and then later clear that if we decide to keep it. And if when we clear it, that's when we'll clear the notes. We won't touch the notes until we've decided we found something.
Can I just, I want to count how many clicks it takes to solve this one.
You want to compare it with the brute force, which is going to be like 1 click.
11 clicks for this one, but I think the brute force it won't increase the number of clicks, or it won't decrease the number of clicks for this one or the easy game. Only the medium game, because that one isn't already solved. We're only going to implement the brute force once we're at a standstill, and we never get to a standstill in this one.
Right. Well, but we'll also have the button there, which means you could just start off and say brute force.
That's true.
So it could drop it to 1 click. Okay, buddy. Let's do it. So let's add a button. You want to do that?
Yeah.
Remember how to add a button in XAML? See if you can figure that out. By the way, to get to the designer, it's an unmain window.
Main window.xaml. No.
Right-click this and choose View Designer.
Oh, it's not here.
Right-click the code and choose View Designer. It's about there. It is. Right up there.
View Designer. Shift F7. Shift F7. So it's just B, right?
You click on but you click on Solve. It'll take the caret right. It'll select it in the code below. See that? You just got to figure out where you want that button.
I think I'm gonna put it right here. Does that fit? Yeah, that fits. And then this one will be.
I like lowercase for my names of opponents on the forum.
Brute force.
Cool.
And then in here, it's just gonna be. Sorry.
You gotta write something. Oh, you're going for recursive. I thought you were going to call it brute force.
Yeah, I think brute force.
Yeah. Alright. Cool. Let me grab the mouse a second. I'm going to just come in here. I'm going to grab this code right here. That's just going to make this, well, it looks like we don't need it actually. Never mind. Alright, we need to get an event handler for that. Do you know how to do that? Do you remember how to create an event handler? Oh wait, we do need it. Hold on, we do need it. See, it's not quite right. We're pasted in right there. And now you see it spaces itself out a little bit more. Okay, we need an event handler in there. Can you help me with that? Good. So now we have the brute, we want to do this. So now at this point, I think I want to call a method called brute force attack is what I want to do.
Okay.
I just want to, that's going to be my starter method. You know, when I have a method. You could type that method in for me?
Yes.
You're like, okay, that's cool. And I'm like, get to work, my friend. Brute force attack.
Attack. Did I spell attack right?
Yep. Open brain, close brain, semicolon.
Nope.
Hit the code rush key, declare it.
Control dot declare or generate.
There it is. Here's our method. This is our beautiful method. All right, we need to iterate through. So let's drop a marker here. Alt home. Control home to get to the top of the file. I think. Yeah. Look at line 24. Let's copy that identifier on line 24. Squares. Uh-oh. I didn't bring my umbrella. No! No!
Pudding!
Come on, Pudding. Never fear. You never have fear. We fear all the time. All right. Got it copied to the clipboard? Notice, what is this, Campbell? What squares?
It is the type of Sudoku square.
It's not the type of it. A type is going to be in green, and this is in white. What squares? So what are those brackets?
Oh, it's like it's a variable of type the array of Sudoku square.
Right, and is that array? Tell me about the dimensionality of that array.
It's a two-dimension array.
Right, it's a two-dimensional array. And how big is it?
It is 9 by 9.
9 by 9. So those are the squares of our board. You've got that copied to the clipboard?
Yes.
Okay, hit escape to get back. Type in FRI in the space bar. This is going to get you a for loop right here. Yeah, let me see. I think that's fair. We can do this. We can start the brute force attack like this, is what we can do. So we're going to go through every square. Okay?
Yes.
Then we need a variable of type square. And to get to the variable of type Sudoku square, I'm just going to type in this here, and I'm going to hit the code rush key and choose declare local. And so that's going to give me the square at any point.
Wait, how did it? Oh.
Oh, wait, shoot. This is two-dimensional.
Yes.
And I've got a one-dimensional accessor, which means this isn't going to work. What I really need to do is I need something more like this. And I need this to be like my row.
And then you need to do another for loop, yeah.
My column, like that, like that.
And then control KD.
And then we're going to say row, comma, column. Like that. Now everybody's happy.
Sorry, that was not what I
you
meant.
want to get the control KD? I'm sorry, I just touched the keyboard key at the same time. Go ahead and switch it down. Control KD. There you go. So that gives us our square. We want to see if it's empty. I want to say, hey, if, maybe do this. If not is empty, I know I don't have this yet, but I kind of want to do it because I like the way the code works. Or maybe just, if we're empty, then continue. No, wait, sorry. If we're not empty, we want to continue. Let's declare this. And we're going to return is empty is true when value is equal to chart.min value. Return value equals this. That means we're empty. Okay? So let me show you this code. This is a property. It's got a default accessor. The word get isn't here. Because we're just going to put it all on one line. It's just shorthand for giving me a property. That makes sense? Property called is empty, and it returns true when this is true. And if this isn't true, it returns this Boolean expression. So if value is equal to char.min value, we're empty. We don't have anything in that. So now I've got this sweet little is empty property, read-only property I can call. So if we're not empty, continue. I'm only looking for empty squares. Now at this point, I have an empty square. Magic! I have an empty square now.
Ooh.
Right?
I still have the notes, so it's not completely empty. But
right. Well, we're going to use the notes. Write down notes. I want those. And I want to use in our, remember our base group solver? It's got that static method. Oh, wait. No, where is it? Where's get notes? I want to find get notes. Get numbers? Base group solver. Ooh, but it's not static. I'm going to make it static. I want to call this from anywhere. So I want to use this in other places, not just in descendants of base group solver. Okay, we call this .get numbers. And I'm going to pass in Sudoku square dot notes. Like that. I'm going to assign it to a local variable. Cool?
Yeah.
Then I'm going to do this. I'm going to say for each number in numbers. Then I'm going to do this. I'm going to say Sudoku square dot value equals, we're going to do that thing we did before, number dot toString, and get the first character of it, which is going to give me that chart. Whoops, I don't need that there. So this is an index order to the string array. Do you remember that? Does that make sense to you, what we're doing there?
Yes.
It's been a while since we talked about that. Okay. So there I'm setting the value, but now what I also want to do is I want to do this. Has test value. I want to set that equal to true. Okay? So I'm going to declare that. Auto implemented. I'm fine with that. So we've now just set has test value to true. We've given it this new value. Now, notice with this loop, it goes through everything in the numbers that it's in the, there from the notes, right?
Yeah.
Okay? Goes through every one. And it just sets the value to that exact same square to each one of those.
Okay.
So if I have 1 and 8 in here, that square's first going to have a 1, then it's going to have an 8.
Yes.
Right?
Yeah.
I need to make a call here. Because if I don't make a call here, this is just going to just repeat. And it's only going to do it in one square, you know, for that empty square. It's going to do it for each empty square, but that's going to be it. I need to make a call here. And the call I need to make is back into brute force attack. Is what I need to do. But because I've now put a value here, right? Because I've made it put a value here, it's going to skip over it when it goes through these. So we're just kind of getting the combos. Now we still have to check to make sure that change is good. Okay? So what we need to do next is we need to say, if square is good, square has no conflicts, and I'm going to pass in row and column to it, like that. Then we'll do the brute force attack. We'll keep going.
Okay.
All right? So that's kind of what we're doing. We're going to make a change here to the square, check to see if it has no conflicts, and if it has no conflicts, we're good to go. Now, I'm thinking somewhere in here we wrote some code about conflicts. I don't remember it anymore. Show conflicts? Notice okay, interesting. So I'm trying to figure out if we can reuse this code or if we can. This is the code that sets the conflicts. It checks for conflicts. It checks for conflicts in the row, in the column, and in the blocks. And if it finds a conflict, it sets it in there.
Yeah.
Yeah. You're totally out of focus. Do you know that you can bring your hand up sometimes to the camera and bring it back? And get yourself back in focus sometimes, so it's kind of like...
Huh? I did not see that. Wait. What? Oh.
Huh. Wait, are you... No.
Nope.
Not working? Let me see what I can do on your camera here. On the video controls. Here's my focus button.
I got it.
You kicked in?
Yes.
All right, cool. You just have to sit up straight? It's a slouch defocus camera?
I had to go back. I had to go forward to the camera and then come back.
Okay. I think... what I want to do is this. I think I want to take all of this. And I want to put it in its own method. It says something like this. Check, maybe, check conflicts. This, R, C. Okay. We'll declare it like this. We'll paste that in like that. This continues to turn into a return. They're essentially the same, but one works from inside a for loop. Well, actually, that's not entirely true, is it? Okay, so in check for conflicts, I want to check for conflicts to return a Boolean. So we change that to a bool right there. And we're going to change this to a false. Like that. And then I want to set a variable in here. What should I call this variable, Campbell? This is going to tell us whether we have conflicts or not.
Huh. Probably is conflict or...
Is conflicted.
Oh, it's conflicted.
That's how I taunt my enemies. You are conflicted. I will say it's equal to false here. And where will I set it to true?
You're going to set it to true when... Well,
look at the code.
Conflict.
Show me where.
What?
Hold on, I'm going to come back in here and I'm going to say, at the end of this, I'm going to say return.
Why isn't the R template working? The return template.
So where will I set is conflicted to true? There I set it to false, so somewhere between there and when I return it, I have to set it to true. Show me where.
When you set this square dot has conflict to true, and also column.
Okay, so I can do it here. Anywhere else?
Also.
Tell me the line number if you want.
452 or
okay.
After 451.
Anywhere else? Whoops. By the way, let me show you how you can do this. Is conflict is on the clipboard, just type in ST and spacebar. Set to true. That's what that means. Okay?
And then also right here.
Yes. Good. So this will tell if it's conflicted. Now, it is marking these and changing. I don't want us to change this when we're calling it from our brute force solver. So I'm going to add a Boolean parameter here called set has conflicted property, and I'm going to set that equal to true by default. So nobody says it does anything. So now what I'm going to do here is ask the question, hey, if that's true, then we're going to change it to that. See that? So if we're going to set it, then we're going to actually change it. Otherwise, we're not going to even worry about changing it. Any questions on that?
No.
Same thing here. So nothing can kind of do two things for us. Okay, so now we've got this check for conflicts. And maybe, I'm going to rename it to has conflicts.
1 second, my headphones are tangled.
What? I didn't hear you.
Sorry, my headphones are tangled.
Okay. Has conflicts. Maybe not. I'm going to call it check for conflicts, but watch what I'm going to do. I'm going to create a second method called has conflicts, and it's going to basically take these two parameters, and it's going to return check for conflicts of R, comma C, comma false. This would be called has conflicts. So now we've got this cool has conflicts method. It calls check for conflicts, and we've got this kind of multi-purpose check for conflicts. All right, cool. So now we want to go back to where we were. Hopefully we've got the marker. Yeah, square has no conflicts. We've got this new cool thing called has conflicts right here. So I'm safe not has conflicts. We don't need this anymore. So if we don't have any conflicts, then we can keep going with the brute force attack. Otherwise, we're going to keep trying these values.
Yes.
Okay.
I think we also need a piece of code that says once we have checked all the values for that square, we go to the next square. If none of... Oh wait, no, because the values will always work.
This code does that. This gets us back in. Right? Ultimately, yes. When the brute force attack is complete, every square should be filled.
Yeah.
And they should be filled with what I think is the right value if our code is right. Do you want to test it right now and see if it works?
Sure. Good. I'm just going to do the simple game first. Oh, it's taking a little bit.
Is it not responsive?
I don't think it is.
No, it looks responsive. You can click on things.
What if I hit solve? Huh. If I hit solve, it works.
Alright, so let's set some breakpoints and take a look at what's going on.
Oh, I just realized. The numbers in here kind of like make a circle in this game, the set numbers.
Yeah, I've noticed that patterns in Sudoku puzzles. All right, so brute force isn't doing anything, it looks like. Let's hit breakpoint. Step inside it. Brute force. Go in here. Boom, 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 boom. All right, so we're going in here first, row and column 0 and 0. Should have taken a screenshot. So we see what's going on there, and it's not empty. Let's set a breakpoint here to see if we get here. Yeah, we do. So what's in this Sudoku square? It has no notes. Okay. Let's set a breakpoint here to see if we get a square with notes in it. Run. No notes. So we need to at least hit solve once before we can do a brute force attack because we don't have any notes. Or alternatively, we could go call create notes for everything if you want.
Okay.
All right, let's do that.
Skype has frozen.
Before the brute force attack.
Skype is frozen.
Okay, you want to do a reconnect on that? Good now?
Yeah, better.
Alright, so let's see. Now what we want to do is before we call the brute force attack, we need something to add notes or something like that. We need the add notes piece. Here, go ahead and take that and drag it off. Basically, we need something that says add notes if we're missing any notes. I forget what the method is called. I want to call it add notes. Let's just type in the word notes and see what we get. Refresh all notes. I'm a little worried about this, Kevin, because I think it actually adds notes that we don't need. I don't know how great it is. I think it's not as smart. But let's try it. Brute force attack. Okay, now we're going in here. Let's see if we hit this breakpoint. Cool. Now we get this breakpoint. So we have 9 notes. I don't think refresh all notes worked I think there's a bug in refresh all nodes. There should be no squares with not all 9. Every block, unless, are there any blocks in here that don't have any numbers at all?
I don't think so.
Yeah.
Wait, let's check.
Here's how we do it.
Wait,
you can't check while it's at a breakpoint. So I have to go in and I'm going to choose disable all breakpoints, and then we can hit run, and now you can check.
It's not letting me open it.
It could be because it's working on it, trying to solve it. It's going through all the...
Well, we can see. This is the simple game? Yeah, it is.
Yeah, there's nothing that should have all 9 nodes.
Yeah. Oops.
You're still locked up?
Yes, it appears.
Okay, do this. Go into the debug menu and choose break all.
Oh, it's starting up and it is, Oh, we didn't load the game!
Oh, we didn't?
We didn't.
Interesting that it didn't come up with a solution. I feel like you totally should have done that. So did you hit load game?
Wait, let me do it.
I thought we did load the game.
Yeah. No, I don't think we did.
Try it again.
Brute force. Brute force.
Doesn't look like it did a very good job, Campbell.
No, it didn't. It's just filling in the last value in all of them. It takes the last value and is just like, yep. Oh, in some cases it's correct. Kind of. We don't know. But
hold on, let me look at it. We got a problem in our recursive method. Let's go look at it. Yeah, so we're going through, let's see, if we don't have conflicts, I think at some point, we might change this, and instead of calling this here, although I like this is really tight, it's like, it has conflicts, just checking that row or the column.
yeah.
If we don't have any conflicts, we're going to continue along the way to the brute force attack. At some point, I think we want to do a check to see if all squares are filled. And I think it looks like this, Campbell. I think it's right here. We need another exit. If all squares are filled, then we want to get out. So let's clear this a second. Let's see what this does for us. If I find any empty square, then we're going to return false. Otherwise, we're going to return true down here. That's all squares are filled. Take a look at that. Any questions on that?
No.
Okay, run.
I don't.
Try running now and see what happens.
Okay. Brute force. Oh, forgot to load the game. Again. Nope, load game. Brute force. Ah!
Still using the last value, every single one. Let's tweak this. Oh, I think I know what I need to do. So if we have got conflicts in this, we've got to go backwards. Oops, sorry. Yeah, I think we're going to have to do this. I wonder if this will have any, let's see if this has impact on it or not. Huh. That's interesting. I hit brute force, but it did not finish.
Weird. Very, very weird.
Now we have notes. I'm not sure I want it to come back in, and I think it could have something to do with the notes. I just hit it a second time. I'm interested to see where it goes. Because we've got notes now when we've set values.
Uh-oh. Something's wrong. Look. This square has no notes. And same with this square.
Mm-hmm. I'm with you. 100%. Yeah, we're not making any changes to the notes. I think we're going to need to get change brute force attack to return true or false, if it's successful or not. I think that's a key part of this. So let's do this. Let's have it return a value. All scores are filled. Then we're going to say return has no conflicts. I'm going to maybe say return true. If all scores are filled, then we're done. I don't think we need to check for conflicts because we're checking them individually here, right in this space right here. And then I want to say if down here, then I'm going to say return brute force attack, like this. So we're going to go back in. If we have conflicts in it, we're going to clear those conflicts.
Genescu 7, where are you? We need your help! Alright.
Brute force, we need brute force attack.
Here, right now.
Welcome, Genescu 7.
Yeah. I think, I'm almost thinking the end looks the same as the beginning of all scores are filled and return true, which means I could just come down in here. I could put it right at the end, like that. I want to try this, Campbell. I'm feeling this is a shot at working. See what happens. Sometimes this happens, right? When you're working with, trying to get this, kind of nudge it into shape. Now approved paths, return value. Oh, okay. Let's return all scores of filled. This point. I'm feeling better about that. And so brute force attack coming down here. Return brute force attack. I feel like I need an if kind of thing here. I do. I think this is if brute force attack works, right? Then I want to break out of this loop. I think part of the reason why we're seeing the end is that this loop executes all the way to the end every time, no matter what. But now I've got it as breaking out of here. That's what I'm going to do. I think that's going to definitely change the behavior. Let's see what happens with it. Let's see I think it's definitely load the game for me and hit the brute force button. See how that works. Click on something to see if we've got, we're still working. Wow! It got that far? And no conflicts, but why didn't it get farther? And now the notes are not right anymore. But we haven't done a secondary stage though where we go through and we clean up. We clean up.
I'm not even sure if any of these notes, any of these values are correct.
I think they are, because we see no conflict highlight. The conflict highlighting is happening automatically. Like you throw a 3 in there somewhere, it'll see the conflict highlighting. Come up, throw a 1 and you'll see, right? It sees the conflicts. It sees those pieces that are there. I think they are right. Hit the solve button. Get rid of that 3 and hit the solve. Well, solve I'm not sure it's going to work or not because of the notes are bad.
Yeah.
Yeah, the notes are bad.
Yeah.
Clear notes. Here,
wait, I think I have an idea. So what if we do brute force, and then we do clear notes,
then solve,
and then we do brute force again.
Sure, we can try that too.
Or
why is it getting out early? It's as if it thinks all of the notes are filled.
Oh wait, it needs notes.
Wait, no, remember brute force adds
right,
at the beginning, I think. It refreshes them.
Okay. Brute force. Where are you?
Are we just waiting for it?
Yeah, I clicked
No, if you can move around, we're not waiting for it anymore. So it's not able to find anything. It's not able to put any notes in either, it looks like. I think we need a refresh notes button to put the notes in and see if that code's working like we're expecting it to. I have an idea. I think his empty's not working. I think value is sometimes set to something else. I think it's set to it might be set to that. Let's see if we can verify that in these setters. Char min value. No, it doesn't look like it. It's only char min value. Okay, so I was thinking empty was wrong maybe because we were setting. I wonder if we ever set the text, but we do get from the text though. We check to see if the text length is greater than 0. I wonder if we ever set the text to like a space or anything.
Huh.
Whoa! There it is right there. This might have something to do with it. I think I want to change it to an empty string instead. Or I could keep it and we could change this piece here. Or length of this is greater than that and text is not equal to space. That might help. Let's see what happens when we run that. I also think the reason it's slow is our text change events are firing and we're listening to all of them as we're making all these changes. And I think we need to ignore those. We need to set and say that, hey, we're working on brute force stuff right now.
Okay. Yeah, it's very slow.
Click on the square until you get it, the caret inside of there. The fact that it's taking longer might be a good thing because that was the only thing I changed. You can also do a break all. Still not working, huh? You're still clicking there?
Still clicking.
Well, let's go try break all. We're getting the value here of this. Okay, let's get out of there and see where we are. Remember that call stack I told you about? Try hitting Control-Alt-C and see if the call stack shows. I can see it. It's the bottom left. Right behind the player. Did you hit Control-C?
Yep.
Let me try it. Control-Shift-C? Nope. Alt-C? No, it works. Hit Control-Alt-C. Try it.
That did not work for me.
Just hold down the Control key, the Alt key, and the letter C.
I did.
There's your call stack. We are deep into brute force attack, it looks like. This is how many levels in we've done. So this is how many numbers we've tried. So we're still going through it. So at this point, I'm feeling like, okay, let's keep it running.
Very slow.
Give it another, moment or two.
Wait, can I?
You can try another break all if you want. See how far we are. Look at the call stack. Bring it up. Control Alt C. See how far it is. Scroll to get a sense of how many layers in. Okay. So it seems like we're going to go deeper. I want to do this. We're setting the value. I think we've got a text change event in here. And I think, here we go, text change. What's the first one here? So, see what's going on? Every time we get text changes, we're coming in here doing a bunch of stuff. Then we're calling on value change. Okay? Here's what I want to do. I think I'm going to create a Boolean property. Pudding solver needed. Okay, I want it. I want to call it updating. Like that. And then all I want to do is when we get here, I want to say, hey, keep updating and get out. Okay? Like that.
Yeah.
Then what I want to do is over here in main window, when we start to do the brute force attack, I want to go grab my that static property. I think it's called updating. Like this. Then I want to put this in the try finally block and then set this to false down here. Like that. And I think it's going to run faster. Let's stop it and let's run it and see if that helps us at all. Excuse me. All right, so you hit brute force.
Yeah.
See how we're doing here. It doesn't seem to be a very significant change. Let's stop on this spot right here too, which is kind of interesting, which implies to me that maybe this is taking a lot more time than normal, right, to go in and make this change. And we might want to make some changes to optimize this for performance. We're not working with a user control. We're instead working with some kind of raw data, which is a better practice to do, but it's just more code. So that's why I avoided it for the show. Let's see what the call stack is. How high is that?
Huh.
Does not seem as high as we got it before, as I recall. Okay, let's keep going. There should be one of those calls nested for every empty square we have. unable to transition because it's taken a long time. We're not responding. I'm going to go ahead and hit continue. I have another idea on how we can speed this up too.
How?
We pass in the starting row and column of the square we just found, so we don't go beyond that. So we don't look at all the ones at the beginning again, right? Imagine if they were all empty and we're filling the first row and the second row and the third row, all of that, right? So it's all empty and we're filling in squares one at a time, like this. Can you imagine that?
Yeah.
Right? Well, every time I fill it in, I have to go check all 99 in front of me, or 81 in front of me to see if they're empty. I'm doing wasted work. Because I know it doesn't have, I know that doesn't, that we don't need to do that work.
Yeah.
I'm going to make that change now. This is still taking a long time. This is taking like too long to like really answer the question. Like I want to know where we are. I'm going to set a breakpoint here. And
it's
where are we at?
like
We're
over
at column
a minute.
6. And row 8 is where we are. Let's keep it going for a little bit more. Let's see where we get next when I set the breakpoint. Row 8 still, column 7. It's taking a while. So, looking at performance, right? Solving performance problems is, I think, going to hit earlier in the show than I thought otherwise that it would do. We clearly have a performance problem here. We're looking at basically numbers. These are fast machines. They should be working much faster. I think it's because we're working with the user controls that we have on there, and we should be working with some raw data instead. It could be also that we've got an algorithm that's problematic. Let's set a breakpoint here. Let's see how we are doing now. The breakpoint here, where are we? We're back to row 1, column 8. So that means we popped out. We found something that was wrong, is what I think. We found a conflict. Let's set a breakpoint there. And actually here, we could save time too by just simply returning true here. And that gets us out. We don't have to do a break there. We can just flat out do a return true. So that's actually interesting, so the break. That might also speed us up. Let me try doing this. Let's do two things. We're going to do this. We're going to change our brute force attack, and we're going to take in two variables here. Starting row, set it equal to 0, and starting column. So you can figure out why I'm doing this. And set that equal to 0 as well. And how I'm going to use these. Watch what I do with starting row. And watch what I do with starting column. And now watch when I call brute force attack. I pass in row and column. So as we get deeper, we're only going to start on the pieces that we haven't worked through yet. Is that going to... We're going to have to do one thing now. Once we get to here, we're going to have to say starting column is equal to 0. So that the next time, so we do one row, we started at that column, but the next row we have to get back to start at 0, is what we have to do. So that's what that's going to do. We're going to make sure that we start at 0 the next time we go in. And I think that's what we need to do. Let's see if those things speed us up at all. Are we just clicking once? Or are we control click? What are we doing?
I think we're just trying to see with the easy game first.
Okay, we found some conflicts. Good to know.
Ooh.
Let's also set a breakpoint here. See if we ever get down to that point. Right there. And another breakpoint, I guess, here. So breakpoint here. What are we at? Row is 8, column 7. That feels good. Seems like we're hitting faster than we've hit before. Another breakpoint. Where are we at? 6, 6. So we've gone back. So we found something that didn't work. That means it has conflicts was here. I'm going to still run it. We can also do this too, because another ways of thinking about this, Kimmel, is each time we add one, we're kind of multiplying the number of possibilities that we have to solve. So the more squares we have to solve, the harder the brute force attack has to work. So if we use our other techniques to partially solve and then run the brute force attack, keep going.
Yeah.
Where are we at? Row 8 and 7. So we're near the end of this, but... And I'm open to the possibility too, Campbell, that my recursive method is not properly designed. It kind of feels right, but you know, the fact that this is taking a really long time...
I think that's just recursion. I think it's taking a long time. It's good.
Running through all the combinations, right? So it's like kind of like 3.
And there are 81 of them.
Let's say there are 3. If there are 3 combinations for each square, it'd be 3 to the power of 81. I think I'm getting this right in terms of combinations. I think. Well,
that's a lot.
Yeah, it's a lot of numbers, right? Like just with like 10 digits at 10 combinations each, right? What's the biggest number you can make with 10 digits? It's like 10 million, right? 10 million combinations. So it's running through all of those. Are we done? Where are we? Row 8, column 7. It's not entirely an indication that we're almost done or not. You really need a sense of what the... Yeah, there's not really any way to really get a sense of how far we are away getting through this. Let's do this. Let's check in the code and keep it running now. And let's see if we get out of here while we're checking in the code. Hopefully it'll do that.
Okay.
So we added the only one solver. There's only one
says if,
note in a group, it has to be in that square. If there's only one, when I say one note, one symbol in all the notes, out of all the notes in the group, it's got to be in that one. Isn't that what it was? That was their logic, I think, right? Then it's THEN.
Oh. Oh, right. Yeah. Okay. Okay. Then that is. Does that make sense?
Not quite to me. I want to change this. We added a rule. Let's just see what we got here. We added a rule called the only one solver,
which says if one. No, that does not make sense.
Let's do this. We'll say we added the only one solver. It says if there is only one
of a number, no,
symbol in all the notes, of a group, then the square holding that note, the value of the square for holding that note is that note.
Yeah.
Is that symbol maybe?
No.
So we did that. We tried brute force. Can you go click on our app? Is there any responsiveness yet?
No.
Any breakpoints? Are we any breakpoints in the code? Can you see that?
Nope.
Nope. Yeah. Brute force attacks require a lot of horsepower, a lot of computer power to do that. All right, we tried our recursive brute force attack, but
that didn't work.
Disappointing results. Well, we don't know if it worked or not actually at this point.
That's true.
What's interesting is, does this actually work at this point? Let's go ahead and finish the check-in now. Also have the brute force attack. Unknown if it's working at this point.
Brute force attack. Unknown if it is working.
All right, I'm gonna get a raid going. I guess I'll tweet about this if we end up finding out that it solved it or not. Let's go back and set a breakpoint before we get out of here. Let's set a breakpoint just right up here. How are we doing? We're still kicking butt in here. We're on 8 column 7. We're going through it.
It's been on row 8, column 7 for a really long time, though.
No, it hasn't, I think. It's just because we've stopped it and it's been there doesn't mean that's where it's been. Remember, there are multiple call stacks here. There are multiple of those call stacks. We can go do this. We can F10, go through this. We just hit return all squares are filled. So my guess is that that's not true. So now that we just popped out, we're at 8.5 is where we are. We could do this. We do have a bunch of test values totally here. We could just simply do this. Hit return true here, which is now going to start returning true all the way through and pop us out. And just take a look at what it's done so far. And if what it's done so far, what we're doing, if you look at the call stack, we're popping out of the call stack each time. So this is how deep we are. So take a look at this. So we'll go all the way up. See what's happening to the call stack? We're taking the top one off of there. See it, Campbell?
Yes.
We're about to find out if it was on the right track or not. So now we're here. We say update is false. And we say run. It looks good so far. But we still got, right? Does it look good to you?
Yeah.
We've got notes that are wrong. We haven't updated notes. We've got a bunch of trial values out there. But at this point, I'm not convinced it's failing yet. I'm just thinking, look, if it's got to go through all the possibilities. So if you look at the notes, it's like 3 times 2, right? There are 6 possibilities of these two. 6 times 4 is 24, times 4 is about 100, times 4 is about 400, times 3 is about 1,000, times 3 again is about 3,000, times 3 again is 10,000. So now just to get these numbers here, there are 10,000 combinations of those. I'm going to try 10,000 different things. And I've only done these. I added more and more and more. We're probably at 1 million combinations by here. We're probably at multiple millions down there. Right? So I'm not convinced it's failing. I just think it needs more time. So I think what we should do is this. I'll go ahead and do the raid. We'll do this and we'll report back on this tomorrow. We'll have this just run and let it stand alone. We'll clear it, we'll load it, we'll hit solve on it, and we'll see what happens. Why don't we look at one we can't solve? Which is that one?
It's control game.
And now hit the solve button on this as many times as you can. So we're starting to cut down those combinations. So brute force has less time to work. There you go, good. And this, hit this.
Let's hit it. Is it?
Okay.
Yeah.
So it's still got, 2 times 2 times 2.
It's got
2 times 2, 32 times 3 is 100 times 3 is 1,000 times, it's got 1,000 times what? That's 4, 8, 24, 50, 100, another 1,000 there. So we're at 1 million combinations to about here still. But we'll see how this works. We'll let you know tomorrow on whether this is able to actually solve it or not.
Yeah.
We might want to have some sort of user feedback as well to tell us how well we're doing. Pudding asked in the chat room, I'm not sure when you guys asked this, Pudding, can we name it Pudding Solver? I'm not sure if we can do that or not, Pudding. We could violate, several laws here in Costa Rica. I'm going to start the raid, get that going. Don't.
Oops.
Yeah, just hit run. Hit continue here. This just says, hey, if it takes more than 60 seconds, I'm worried. We might also count, we can do this tomorrow, we'll look at performance, we'll look at feedback on it. We'll see ultimately if this was working or not. I think there's a chance. There's a chance it might work. We'll start the raid. We'll send you over to InstaFluff. Started it. Let's try one more time.
Okay. It's been named Pudding Solver.
What'd you say?
It's been named Pudding Solver.
Okay. Hold on a second. I need to. My raid's not working. Let me refresh the screen here and find out why the raid's not working.
Wait. Is it okay if I stop it?
No. Why would you stop it?
Because it's not being responsive at all.
What?
It's not being responsive at all. Like I can't.
Right, because it's running. It's going.
Okay.
Looks like I'm gonna have to manually raid InstaFluff. Let's type that in. Raid InstaFluff. Is that gonna work? You cannot raid this channel. Interesting. Let's try one more time. Cannot raid the channel. I'm taking the cache and doing a hard refresh over here in the Stream Manager. Try one more time.
Câu vào tháng rồi.